Hi, chemistry guys and gals. I wanted to take a few minutes and in this video go through the chemistry math pre-assessment. Again, these skills, especially 1 through 8, are pretty much basic math that you'll be expected to know and be able to use prior to taking chemistry. So just keep that in mind and be sure to contact me if you have any questions or concerns about whether or not you should continue in the course this year. So in front of you, you see the pretest. And again, it's wrong answers don't count against you. We just wanted to go through and review and see how well you did. Number 1, looking at the expression, you basically need to find the value. And so we're going to start with that in parentheses. We're going to use an order of operations PEMDAS. So that which is in parentheses is going to come first. So 7 minus 4 is 3. And then there are no exponents, so we're going to multiply next. So 3 times 2 is 6, and then, of course, addition and subtraction last. So plus 3. So again, 7 minus 4 is 3, times 2 is 6, plus 3 is 9. So we'll go ahead and mark that value as the correct answer, A, or 9. As we look at number 2, we're working with exponents. 2 raised to the 4th power means 2 times 2 times 2 times 2, or 2 times itself 4 times. And the value of that is 16. If you're working with very large exponents in such an expression, you can always use your calculator. Let's say it was 2 to the 16th power. So on your calculator, you would enter in 2 yx and then raise it to the 16th power. So 2yx to the 16th, for example, is 65,536 on my calculator. And you should familiarize yourself with how to use your calculator for exponential functions. Number 3 is asking us to write numbers in scientific notation. In scientific notation, you write one and only one non-zero number to the left of the decimal. And it helps us then to recognize which numbers are actually part of the measurement. So if you measured a value on, let's say it was on a really fine balance and it came out to be 0.000786 grams, and you needed to report that number, you would report it as 7.86. When you do so, you're moving the decimal place there where you see my cursor's moving between the 7 and the 8. And so what you do is you count over 1, 2, 3, 4 decimal places, and we're making the number when we write 7.86 look much bigger. So that it means it's going to have a negative exponent, and it's going to be written 7.86 times 10 to the minus 4. On number 4, the first thing I do usually when I solve mathematical expressions is to resolve the units first. This is a procedure which your math teachers may have referred to as dimensional analysis. By checking the units and making sure they come out in the unit that's correct that you're looking for, you will be able to preview and take a look ahead to see whether or not you've set the calculation up properly. So when I see that I have centimeters to the 3rd power, or centimeters cubed, and I'm dividing it by centimeters squared, I know that I am going to end up in just centimeters. Or if you paid attention to the video that I had you watch today, then what happens is you take the bottom exponent and subtract it from the top. So 3 minus 2 is 1. So that should be centimeters to the 1st power. And of course, all answers give a numerical value of 3. Oopsie, sorry. Didn't realize my cursor was going to do that. I'll go back to using my stylus. And so the correct answer is B. If 2a equals 3b and a equals 6, what does b equal? So if you just substitute 6 in for a, 2 times a, or 2 times 6 is 12, equals 3b. So divide 12 by 3 and you get 4. So the next part then is the one that I think is one I got several questions about, and this is um, how do we rearrange variables in order to solve for the unknown variable? And it's important to remember that just like when you're working with any mathematical expression that contains numbers, variables work the same way. So when you see an equal sign, the equal sign means that what is on the left is equal to what is on the right. So even though we can rearrange the variables in such a way as to isolate one variable, we have to do the same thing to both sides of the equation in order to make sure that we are accounting for the fact that both sides must remain equal. So if you're starting with density equals mass divided by volume, and it's asking us to solve for the variable v. I don't like that v is on the bottom on this side, so I'll just multiply both sides by v. And then what happens is I'm going to get mass equals density times volume, or volume times density equals mass, because again, they're interchangeable. It's like 2 plus 2 equals 4 is the same as 4 equals 2 plus 2. But I have not isolated volume. So now what I'm going to do is I'm going to divide both sides by density. And what happens is when density cancels out here, I end up with volume equals mass divided by density. Number 7, I believe, number 7 I went over in class for most of you, but if the denominator is greater than the numerator, the number on bottom is bigger than what's on the top, you're going to end up with a fraction that's less than 1. And so it's just like, if the numerator is 2 and the denominator is 5, then the fraction is 2/5, and the actual value then is 0.4, or less than 1. In number 8, the cube, they're asking you really how many small cubes are there in the larger cube. And so since it's 3 by 3 by 3, it's 27. All right, so when we go back up to number 9, you saw in the pretest I simply created a value just asking you, instead of measuring this, how would you, or which one is reported to 1/10 of a centimeter, and so you just had to pick that out. Measurement is something that we will pick up later on, and we're gonna have to pay really close attention to measurement in chemistry, because it's very important that if your measurement, excuse me, is valid, your measurement is valid to, there we go, 1/10 of a centimeter, that you report it to 1/10 of a centimeter, even if the number that belongs in that 10th place is 0. And it's also imperative that you don't report any numbers beyond that 10th place, because in chemistry we are concerned with the significance of each digit, numerical digit in the measurement, because it tells us about our accuracy, our degree of accuracy, and our precision in our measurements. So we will discuss this thing called significant figures much more at a later date, but that's just keep in mind when you're making measurements, you're always going to want to go as many as you can on your measuring tool reasonably, and even if one of them is beyond the mark. So if I had a ruler, for example, that measured in centimeters, let's try and get these even, and the marks in between here and here was only at 0.5 centimeters, I would want to be able to go, they're really uneven. Let me back up. Okay, so if my ruler that I'm measuring with is in centimeters, and the marks on the ruler, it's like old school, it only has half centimeter marks. And I can see, obviously, that it's more than 1, more than 2, more than 3, more than 4, more than 4.5, but not quite 5. So the limit of the measuring tool is 0.5. I'm going to go one beyond and say that it's 4.7. That's reasonable for me to say 4.7. It would not be reasonable for me to say 4.75 or 4.65. It's just what I can gauge with my eyes is reasonable, and so that's how we make our measurements. As we read the volume of the water in a graduated cylinder, we have to take into account the differences between those measurements. Let's say this was 10 and this was 11. And how many marks are there on the graduated cylinder? And let's say that on this graduated cylinder, there are 10 marks in between. And when we look at the water level, it's not quite 10.5. In this case, it's maybe just a little bit below 10.5. Doesn't completely match the question that I gave you on the test, but that's something that you need to take into consideration. So you know it's not quite 10.5, but you know it's more than 10.4. So you're going to say 10.48. And see, in that instance, we can go the extra decimal place because we have 10 marks in between. So we'll come back to measuring and take that up again at a later date. Now, vocabulary we should be able to go through fairly quickly. If a variable x is directly proportional to y, it means that y increases when x increases, and vice versa. Spontaneous means that it happens naturally without having to have an outside influence. So if it doesn't happen typically, but sometimes earthquakes happen spontaneously, sometimes avalanches happen spontaneously. Now, an outside influence could speed it up, very much like an outside influence or applying an outside influence could affect the rate of a chemical reaction, but if a reaction occurs spontaneously, that means it's going to happen in nature. Number 13, volume is, of course, base times width times height. So we are looking for a unit value that is cubed, since it's a measurement of distance, and it's cubed, or length, and it's cubed. So we take length times width times height. If we measured it in feet, then it would be feet cubed. If we measured it in centimeters, which we could, it would be centimeters cubed. So where it says centimeters by itself over here, that's not valid. Go back here. And outside influence. Okay. So the only one that's valid for a unit of volume is C, cubic feet. Number 14, which of the following is a hypothesis? Okay, a hypothesis usually takes the form of an if-then statement, which is one thing that you can you can look for. One thing happens, the other is a consequence of that one thing. So the beaker weighs 4.65 grams is just a fact, not a hypothesis. When two solutions were mixed, they turned into a solid. Okay, that is an observation, sure, but it doesn't propose a reason as to why the second thing happened. So let's look at C. The liquid turned to solid because there was a change in the molecular structure. That sounds like a hypothesis. Now, in order for it to truly be a hypothesis, it would have to be testable. But I'm going to go ahead and mark that one, and then if we could test it, it would be a hypothesis. Otherwise, it's just conjecture. And finally, the solid turned back into a liquid when it was heated. And again, that is an observation, something factual that happened. Number 15, aqueous solution is one that is dissolved in water. And the way to remember that is to look for that root word, aqua. And that means, obviously, we know agua, aquafina. These are both aquafina is Latin, and agua is the Spanish word, which comes, Spanish is a romantic language from the Romans, which is Latin. The Romans spoke Latin. Alrighty, so this next one was a little bit tough. An ounce is to a pound. Now this is what I know. I know that there are 16 ounces in 1 pound. So which one's bigger? Well, the pound is bigger. So 16 ounces in 1 pound, okay? And ounces to a pound, that's the relationship that we see. As a centigram, which a centi means 1/100th or 10 to the minus 2 grams, is to which? Well, it wouldn't be a centimeter. Would it be an ounce? Probably not, because when we look at ounces to pounds, they're both part of the same system of measurement, which is the British system. But centigram and ounce, centigram is in the metric system and ounce is in the British system. So that's going to leave us milligram and gram. And that was actually pretty, a little bit difficult to determine, because you might have put milligram, but a milligram is 10 to the minus 3 grams, whereas a gram is just 10 to the 1 or 1 grams. So to be the best analogy, we would want to choose B, gram, because a centigram is smaller than 1 gram. So let's move on to the abstract reasoning questions. This biology student conducted an experiment to find out how light and plant food affected the growth of a particular type of plant. She grew 4 plants and she treated them differently. After 3 weeks, the plants looked as shown. Study the growing conditions and the drawing and answer the questions 17 and 18. So again, first look at the drawings. Obviously, A and B grew bigger than C and D. And how were the conditions the same or different? Well, in 2 different ways. They were in different conditions of light. 2 of them were placed, A and C were placed in the dark, where B and D were in the light. And they were also in different nutrient conditions, where A and B got plant food, but C and D did not. Now we see differences between these plants that were both in the dark, where one got plant food and the other didn't. Now we see differences between the plants that were both in the light, where one got plant food and the other didn't. The problem is, what kind of conclusion can we draw from that? What conclusion can we draw based on the data that's given in the pictures describing the experiment? Does the experiment show that both light and plant food affect the growth of the plants? It doesn't show that light alone affects the growth, because we have differences between dark and light in A and B, and they grew the same, and C and D, and they grew the same. So what it does show is that there's a difference between plant food. That seems to be the primary difference that we're looking at here. And that is why the correct answer is the greatest factor affecting the growth in this experiment was plant food, not light. I mean, I find it hard to believe, but it's possible. Number 18. Show the effects of plant food on the growth of these plants. We should compare, and again, we're gonna want to look at the plant food versus no plant food. And, you know, we could either look at A compared to C or B compared to D. So where are our options here? A and D? And do I see B and C? Nope. So A should be the only correct answer possible. For 19 and 20, we're looking at an experiment in which chemistry students designed this experiment to see how different metals react with strong and weak acids. So strong would be concentrated and weak would be dilute. And they took small metal filings of either copper or iron, and they put them into beakers containing different concentrations of different acids, hydrochloric and sulfuric. So the top right here, that's giving us the sulfuric acid, and the bottom, whoops, I thought I changed the color here. The bottom there is hydrochloric. So A, B, C, and D compares sulfuric acid, both dilute and concentrated, and E, F, G, and H are using hydrochloric. So if we wanted to observe the effects of, and keyword here is different metals, we would need to look at the ones that have the same acid treatment but different metals. So A to B, C to D, E to F, or G to H. Okay, and so the only one that I see that's correct there then would be A. All right, so I'm letting you think about that. We have to make sure that they got the same treatment with the acid and they were different metals. So those are the only combinations that work to answer that question. So A is the only correct answer because it's the only one that has those groupings together. Now 20, which of the following would be the correct procedure for the students to follow to compare E and H to see if reaction rate depends on the strength of an acid? No, we can't compare E and H, and let me show you why. Let me see if I can get some other colors in my palette here. Let's do this one. So if we compare E, really? E is iron and H is copper. So while one is dilute hydrochloric and the other is concentrated hydrochloric, that's not going to work for us. So what if we compared A and D? Well, it's the same deal. One is iron, one is copper. So A to C, that would be iron and dilute sulfuric versus concentrated, to see if it depends on the strength of the acid. That one seems to make sense to me. And then I always go and double check, make sure the last one doesn't match as well. A to H, no, because we're comparing dilute sulfuric to concentrated hydrochloric, and we cannot determine based on the strength of the acid if the strength of the acid is what makes the difference if we use two different acids, because it could be the fact that they're different acids and one of them is just naturally stronger or more reactive than the other with that particular metal. All right, so let's look at 21 and 22. When baking soda is added to vinegar, we see the following chart. The x-axis, the independent variable, the one that is controlled by the experimenter, is the grams of baking soda, and we see that it goes up in 5 gram or 0.5 gram increments. So each beaker, I believe is what they said, they're adding a different amount of baking soda. And what they found is that when they put a balloon on the top of the beaker, they captured a certain amount of gas. And what happened was the amount of gas that they captured went up from 0 to 1.5 steadily. Okay, then it still continued to go up, but it slowed down a touch between 1.5 grams of baking soda and 2 grams, and then it remained the same after, as long as they put 2 grams in. They used a constant amount of vinegar, which was 25 milliliters in the test tube, sorry, not beaker, in order to capture the gas. So which is a valid conclusion? The amount of gas produced increases as the amount of baking soda increases. Well, it was that part was valid up to 1.5, but then it didn't happen thereafter, so we can't make that conclusion. We may need to repeat the experiment with a larger amount of vinegar in the test tubes and make sure that the baking soda remains what's the limiting factor. But it looks like we ran out of vinegar to react, and that was what caused the slowdown. But we can't make that conclusion definitively until we repeat the experiment with excess vinegar. Adding more baking soda than 2 grams does not result in additional gas production. Kind of true. The amount of gas depends only on the amount of vinegar. No. So, and there's obviously clearly a relationship. So B is the correct answer there. Number 22. What would be a valid conclusion if the student had added only, there we go, between 0.5 and 1.5 grams of baking soda? And so then we could go back and make that conclusion A, that the amount of gas produced was dependent on the amount of baking soda. 23 is a math problem where you have to create the algebraic equation to solve it. So for 23, it says if brass is 25% or a quarter by weight of copper, and it should really say by mass, but by mass or by weight of copper, how many grams of copper are in 12 grams of brass? So brass consists of copper as well as other metals. It's an alloy. And so when you look at a mass of 12 grams of brass, put that over 1, only 1/4 of it is copper. So if solving the equation, 12 divided by 4 gives us 3 grams. So the answer is A, 3 grams. 24, a student used a plain piece of paper such as this one and cut out 2 figures. A circle with the diameter of 4 inches. Let's assume that's a perfect circle. Or a square with a diameter of 4 inches. And then we put those on a balance and we saw which one had a greater mass. The square would weigh more because it has more paper, has a greater area, greater surface area there. 25, the biologist used a microscope to measure 2 different kinds of cells. Cell A was 12 micrometers in diameter and cell B was 20. So the ratio of cell A to cell B is 12 to 20. And took a photograph, but in the photograph, when she printed it on the printer, cell A measured 15. So what would cell B measure? So we can do the math there. And so you multiply 20 times, let's do it like solve it. Go 12x equals 15 times 20. We're cross multiplying to solve the proportion. So we take 15 times 20 and then we'll divide it by 12 and that'll give us 25. That's a good one. Okay, so question number 26 says, construct a graph that represents the distance of a car moving at 60, that distance a car moving at 60 miles per hour will travel. Okay, so the easiest way to construct this graph is to start the car at distance 0 miles, and after 1 hour it's going to go to distance 60 miles, and after 2 hours it will go another 60 miles, or to distance 120. And then whenever you create 2 points, you have made a line. And so what you see is a line with a positive slope. And that is how I came to answer question number 26. Thanks for watching.